Imagine you are trying to lay down tracks for a state-of-the-art high-speed rail network. But there's a catch. The train you're building this for is already barreling down the tracks right behind you. It's entirely self-driving. And get this, a completely separate group of people is actively trying to hack the brakes while you work.
Right. And, just to add to the pressure, that autonomous train is moving faster than human reflexes can even manage, which means the infrastructure itself has to, anticipate where it's going.
Yeah, that is the exact feeling of working in tech right now.
Yeah.
So, welcome to the deep dive. Whether you are a cloud architect building out those tracks, a cybersecurity expert trying to, secure the brakes, or an AI and ML practitioner designing the self-driving engine, today's mission is custom tailored for you. We are going to get you completely up to speed on an incredibly dense stack of tech updates from July 10th, 2026. Now, quick piece of housekeeping right up front. This summary was created using Notebook LM, but everything we're about to discuss is based entirely on actual public sources, core data points, and real-world architectures from this week's news.
Right, and when you lay all these seemingly disparate updates out on a table, they paint a single cohesive picture of our current landscape. I mean, we are building hyper-optimized, massive cloud infrastructure specifically to support an entirely new era of autonomous AI software.
Yeah.
And simultaneously, we're frantically scrambling to secure our enterprise networks against the very same automated capabilities we're inventing.
Okay, let's unpack this, starting with the raw horsepower, because, well, none of this works without the physical infrastructure.
Exactly.
If you're managing large-scale infrastructure, you already know that to run advanced AI, you need systems that don't just scale vertically. They have to be completely unbottlenecked. And Google's latest announcement is the perfect example of this philosophy.
Oh, absolutely.
Their C4N virtual machine family is now generally available, or GA. And these are built for x86 workloads that require incredibly intense I/O, which is just, input-output data transfer.
Yeah, and the specifications here are doing a lot of heavy lifting. I mean, we are looking at 400 gigabits per second for VM-to-VM bandwidth.
Wow.
And a staggering 95 million packets per second. And when architects pair these virtual machines with Google's Hyperdisk Extreme, they're hitting 25 gigabytes per second bandwidth and a million IOPS input-output operations per second.
Okay, let's ground those numbers, because just throwing out 95 million packets per second can start to sound like white noise.
Fair enough.
I was trying to visualize the architectural shift that makes this possible, specifically Google's titanium offload silicon. Think of a massive high-end restaurant kitchen on a Friday night.
Okay, I like this.
The 5th-gen Intel Xeon processor is your head chef. In legacy systems, that highly paid head chef was also chopping onions, washing dishes, and taking out the trash.
Right, meaning the CPU was forced to manage the network routing, the virtualization layers, the storage overhead.
Exactly. And because of that overhead, you were essentially wasting expensive compute cycles.
Yeah, but the titanium silicon fundamentally changes that dynamic. It operates like a highly trained army of sous chefs handling all that prep work.
Yeah.
They manage the storage and networking, which means your head chef, the Xeon processor, can dedicate 100% of its cycles to the actual computing workload.
So if you are a cloud architect listening to this, you no longer have to over-provision expensive compute instances just to, absorb the hit from heavy network traffic. Your compute does compute, your network does network.
Exactly. And when you're dealing with massive data lakes or distributed file systems, which are the foundational data layers feeding enterprise AI, your bottleneck is rarely the CPU anymore.
Right, it's the data movement.
Exactly. It's how fast you can move data into and out of the processor. By offloading that I/O overhead to custom hardware, Google is maximizing compute efficiency at the exact moment AI is demanding every spare cycle.
Now, speaking of moving massive amounts of data without bottlenecks, Amazon just dropped an update for Aurora DCQual. Their Change Data Capture, or CDC feature, is now GA.
This is a big one.
Yeah, it automatically captures all inserts, updates, and deletes happening in your database and feeds them directly into Kinesis data streams. But I read the source material, and I have to admit I am skeptical about one specific claim.
The performance tax.
Yes. They're advertising this with a 0 performance tax. Wait, how is it possible to capture and stream every single database modification in real time with absolutely 0 impact on transactional performance? I mean, how is that not just marketing magic?
It sounds like magic, for sure, but it's actually a brilliant architectural separation. You see, traditionally, if you wanted CDC, you had to rely on database triggers or heavy polling mechanisms.
Right.
The problem is, those mechanisms compete for the exact same database engine resources that your primary transactions use. So if you have a massive spike in e-commerce checkouts, your CDC polling could literally slow down a customer's payment process.
Which is like the nightmare scenario for any database administrator.
Exactly. So Amazon solved this by engineering a streaming engine that operates alongside the core workload rather than inside it.
Oh, interesting.
Yeah, it captures the data modifications down at the storage layer. It's physically separated from the primary database execution path, meaning the database engine doesn't even know the CDC capture is happening.
Okay, so if you're building an event-driven architecture, you can trigger a Lambda function, sync an external microservice, or pipe your live data straight into Redshift without risking a single millisecond of latency on your main application.
Which is the holy grail for downstream analytics. But, opening up these massive unbottlenecked pipelines of real-time data creates a glaring problem.
Security.
Exactly. How do you secure them? If data is flowing flawlessly, you need granular control over who or what is allowed to tap into that stream.
Which brings us directly to Azure Event Hubs. Their network security perimeter, or NSP support, is now GA. For the platform engineers, this creates logical security boundaries around your platform as a service resources. It gives you granular control over exactly which external resources or IP addresses can talk to your Event Hub namespace, heavily mitigating the risk of data exfiltration.
Yeah, and there is a critical caveat hidden in the documentation here that architects really need to circle.
Okay, what is it?
To get the full multi-perimeter functionality and the advanced access rules, you absolutely must use Microsoft Entra ID authentication. If your legacy systems are still relying on shared access signatures, those SAS tokens we've used for years.
Oh yeah, the static ones.
Right. Well, these advanced perimeter features are explicitly unsupported for SAS tokens.
Wow. That feels like Microsoft drawing a hard line in the sand. I mean, they're actively pushing enterprises away from static tokens and toward dynamic, identity-driven security constraints.
It's a deliberate forcing function. The cloud providers know that static tokens are a massive liability in an automated threat landscape.
And that reality is the perfect pivot point. We are building these massive 400 gigabit pipelines and zero-tax databases, but we're being forced to build giant identity-secured walls around them because, frankly, the threats are evolving at a terrifying speed.
They really are.
The Cloud Security Alliance just published a stark warning about a phenomenon they're calling the AI storm. They're highlighting how AI is accelerating both vulnerability discovery and exploit development, but I want to push on this. We've been talking about zero trust and network segmentation for almost a decade.
Right, it's not a new concept.
So what makes this AI storm any different from the usual vendor doom and gloom warnings?
The difference comes down to the total collapse of the vulnerability timeline. Historically, when a zero-day vulnerability was disclosed, defenders had a window of time.
A grace period, basically.
Exactly. It might have been a few days or even weeks before a reliable, weaponized exploit was developed and deployed at scale by attackers. You had time to test and deploy a patch. AI fundamentally erases that window.
Completely erases it.
Yeah. Today, AI models can analyze a newly released patch, reverse engineer the vulnerability it fixes, and generate working exploit code in hours, sometimes minutes.
That is insane. So the moment a patch is announced, the race is over before human security teams even get their boots on.
Yes. Because attackers now move at the speed of software, flat corporate networks have become an existential threat.
Because there's no friction.
Right. If an attacker breaches your perimeter and you have a flat network, an AI-driven attack can move laterally across your entire infrastructure, map your assets, and deploy ransomware faster than a human analyst can even acknowledge the first alert.
Wow.
So rigorous phased network segmentation isn't just a best practice anymore. It's the only way to physically contain the blast radius of an automated breach.
You essentially have to design your network assuming the perimeter is already compromised. Like, if they break the lock on the front door, every single interior door better already be deadbolted. And speaking of compromises, NIST just released SP 1326. This is a due diligence quick start guide for cybersecurity supply chain risk management. It breaks vendor evaluation into 5 core components: supply chain tiers, FOCI, which stands for foreign ownership, control or influence, provenance, stability, and foundational cyber practices.
And out of those 5, provenance is the one causing the biggest operational shockwaves right now.
Why is that?
Because the NIST framework is pushing organizations to operationalize the validation of where product actually comes from. We are talking about tracking the physical hardware manufacturing facilities, the software development locations, and rigorously enforcing the use of software bills of materials, or SBOMs.
But let's be real for a second. If you're a CISO at a mid-sized enterprise, tracking the literal manufacturing facility of a silicon chip inside a vendor's server sounds, well, impossible without a massive compliance team. How do you actually do that?
You do it by forcing the burden of proof onto the vendor during procurement. You leverage automated tools to parse those SBOMs. The goal isn't manual auditing. The goal is to catch tampering, counterfeit risks, and hidden third-party exposure before the vendor onboarding process is even finished. You want the automated flags to trip during the contract phase, not 6 months after the vendor is already deeply embedded in your environment.
It's a massive cultural shift from trust but verify to cryptographically prove it before we sign.
Exactly.
Now, alongside supply chain tracking, there is a new CISO's guide to post-quantum mandates. And I'll be honest, quantum threats often feel like a distant sci-fi problem. For the last 5 years, quantum computing has always been 5 to 10 years away. But this guide is demanding action right now.
Yeah, it's demanding action today because of a strategy called Harvest Now, Decrypt Later.
Right.
Even if a viable quantum computer is a decade away, attackers are currently scraping and storing massive troves of encrypted enterprise data. When quantum computers mature, they will retroactively decrypt all of it.
Which is terrifying.
Yeah. The transition to post-quantum cryptography, or PQC, will take years of infrastructure overhauls, which is why the blueprint breaks the migration down into 3 actionable buckets for leadership.
Okay, right, the 3 buckets. First, you have what the major cloud providers will upgrade automatically for you behind the scenes. Second, the commercial off-the-shelf software that must be actively replaced or updated by your IT teams. And third, the legacy systems and custom internal applications that your firm owns directly, which will require heavy cryptographic engineering.
Categorizing it that way stops organizations from trying to boil the ocean, but the guide stresses that the ultimate goal isn't just checking a PQC compliance box. The mandate is to build what they call continuous cryptographic telemetry.
Hold on. Setting up automated monitoring pipelines to track exactly which encryption algorithms are being used across thousands of enterprise endpoints sounds like a multi-year nightmare. Where do you even start with that?
Well, you start by integrating cryptographic discovery tools into your existing vulnerability scanners. And yes, it is a heavy lift, but the payoff is immense. You're building the governance muscles to rotate keys and update protocols seamlessly across your network.
I see. Because if you have the telemetry and agility to swap out algorithms easily for the quantum threat, you can do it for literally any future cryptographic vulnerability.
Exactly. And, if we connect this to the bigger picture, we are building these rigorous defenses, the segmented zero trust networks, supply chain SBOMs, the cryptographic telemetry pipelines, specifically because of the staggering autonomous AI advancements we are seeing on the software side.
It's all connected.
It is. The unbottlenecked cloud infrastructure we started with today is the foundation for a massive shift in how AI operates.
And that shift is wild. So let's dig into the AI and ML frameworks. Amazon's SageMaker HyperPod just made disaggregated prefill and decode generally available. For the ML engineers listening, this means decoupling the compute-heavy prefill operations from the memory bandwidth-bound token decode phases and assigning them to completely dedicated GPU pools.
Yeah, and to really grasp why this optimization is so brilliant, we have to look at the mechanics of how large language models generate text.
Okay, break it down.
The prefill phase is when the model processes your entire initial prompt. It requires massive parallel compute power.
Right.
Then the decode phase is when the model actually generates the response, predicting one single token at a time. That phase isn't heavily reliant on raw compute. It's bottlenecked by memory bandwidth, how fast it can access the model's weights.
I think a good way to visualize this is comparing it to reading versus writing. The prefill phase is like a human sitting down to read an entire 500-page novel all at once to understand the context. It takes an enormous amount of mental energy.
Yeah, great analogy.
But the decode phase is like writing a summary of that novel, one single word at a time. It doesn't take as much raw brain power, but you can only write as fast as your hand can physically move across the paper.
That is a perfect translation. In legacy unified setups, if a user submitted a massive 100,000 token prompt, the system would hit that reading the novel prefill phase and completely hog the GPU's compute resources.
Oh, see.
This would cause the concurrent token generation, the decode phase, to literally stall out for every other user on that hardware.
So by splitting them up into dedicated hardware pools, Amazon completely eliminates that resource contention.
Precisely. Long context requests are routed to the prefill cluster, completely bypassing the decode cluster. This means AI teams can now look at their specific production workloads and scale their prefill and decode hardware independently, saving a fortune on infrastructure costs.
That is a fundamental change to the unit economics of running large language models. But, while Amazon is optimizing the hardware layers, Microsoft is optimizing how the AI agents actually work together.
Yeah.
The Microsoft Agent Framework 1.0 is now GA across Python and .NET. And they've introduced something called agentic orchestration. It essentially means developers can spin up a manager agent that handles multi-round planning, and that manager delegates specific tasks to specialized expert agents.
It's incredible.
Wait, so we are deploying entire corporate hierarchies of AI bots that delegate work to each other?
That is exactly what is happening. We're moving past the era of human-to-chatbot single prompts. Developers are being standardized architectural layouts for group chats, sequential pipelines, and complex handoffs between AI specialists.
Wow.
You are literally building an org chart in code. A manager agent receives a goal from a human, spins up a SQL expert agent to pull data, hands that data to a Python expert agent to analyze it, and then has a visualization agent build a chart.
And because Microsoft is building these high-level standardized workflows, developers don't have to reinvent the wheel. But the advanced ML engineers still have access to the low-level primitives, like raw event streaming, if they need custom routing.
Exactly, and Google is moving in the exact same direction. The Google Cloud Marketplace just made AI Agent as a Service GA.
Right.
They're utilizing the agent-to-agent, or A2A protocol. This allows third-party agents built by different companies to expose their skills to each other using standardized JSON agent cards.
Okay, but if I have a third-party AI agent trying to talk to my internal enterprise AI agent, how does the authentication work? You can't have a human manually typing in passwords every time a bot wants to share data.
No, you can't, which is why Google is heavily utilizing dynamic client registration, or DCR, via cryptographically signed JWTs JSON web tokens.
Okay, translate the acronym SOUP for us. What does that mean for the enterprise deployment?
It means we're establishing machine identity. These autonomous bots can natively authenticate themselves and securely execute tasks inside a corporate environment without a human ever having to manually click approve or manage the handshakes.
Oh, wow.
Yeah, the bots verify their own cryptographic identity securely with the enterprise provider, ensuring that only authorized agents can access internal APIs.
So developers are building these massive, authenticated agent pipelines in the cloud. But what happens when we unleash that same autonomous capability directly onto an end user's laptop? Because OpenAI just launched GPT Live, and it is officially GA.
That's a huge shift.
It uses a full duplex architecture, meaning it processes audio in parallel. It can listen to you and speak to you at the exact same time, handle mid-sentence interruptions naturally, and make microsecond decisions when you pause.
Yeah, the shift from walkie-talkie style turn-based constraints to full duplex is a paradigm shift in human-computer interaction. It forces the system to act socially, not just computationally.
Right.
But under the hood, the dual-model back-channel routing is the real technical marvel.
Right, where hands-off complex reasoning tasks to a background GPT 5.5 model while keeping the voice conversation going. It's like having a conversation while simultaneously doing complex math in the back of your head. You don't stop talking, you just asynchronously farm out the heavy lifting.
Exactly. It keeps the low-latency conversational model at the forefront, so the user experiences zero lag, while the background reasoner works on the actual problem.
Here's where it gets really interesting. OpenAI didn't just update the voice model. They released ChatGPT Work, which merges their Codex coding engine into a desktop app powered by GPT 5.6. It features computer use and scheduled tasks.
This is the game changer.
This AI can literally take control of your local desktop. It can click buttons, type text, move files around your local drive, and monitor your Slack in the background while you are away from the keyboard getting coffee. Oh, and they also launched a sites beta where you can build full web applications using just natural language.
It is no longer a tool. It's functioning as a true autonomous agent. It can break down a complex, multi-step goal, utilize a built-in headless browser to search the web, and execute workflows across your local desktop applications as if a phantom employee were sitting at your desk.
And Meta's counterpunch to this is MuSpark 1.1. It boasts a 1 million token context window and aggressive multimodal reasoning.
Yes, and their approach to this computer use trend is slightly different. MuseSpark utilizes a hybrid model. It actively evaluates your desktop environment and makes a judgment call. Is it faster for me to write a background Python automation script to accomplish this task, or should I just dynamically take control of the mouse and click through the user interface like a human?
That is wild.
Yeah.
It decides its own mechanism of action based on efficiency. I read that it will even take automated screenshots of the web apps it is building, use its vision model to identify visual rendering bugs on the screen, and then rewrite its own code to fix them without any human prompting. It's closed-loop software engineering.
Exactly.
Okay, but think about the implications of this for a second. We have bots writing their own scripts to click our buttons, monitoring our secure enterprise Slack channels, and natively authenticating to talk to other bots in the cloud. If an autonomous agent hallucinates, takes over my desktop, and accidentally deletes a production database, who is legally and operationally responsible?
What's fascinating here is that the security industry is already anticipating that exact nightmare scenario.
Really?
Yeah, the Coalition for Secure AI, or COSAI, just published their Shared Responsibility Framework v1.0. It is a 5-layer model that explicitly divides security ownership across the entire AI supply chain, from the foundational model builders like OpenAI and Meta, all the way down to the deploying enterprise organizations.
So it eliminates the finger pointing when things inevitably break.
Exactly. It specifically tackles non-deterministic behavior. When an AI agent does something entirely unexpected, which by definition it eventually will, this framework dictates exactly who was supposed to build the input and output guardrails and who was supposed to ensure the infrastructure isolation to prevent that blast radius we talked about earlier.
That makes sense.
They even provide a 12-month implementation playbook for enterprise teams to map out their vendor contracts and run tabletop exercises based on agentic failures.
Incredible. It all ties back together. So let's recap this journey we've been on. We started with the sheer physics of the cloud Google's titanium silicon pushing 400 gigabit networks, and Amazon creating zero-tax database pipelines so AI has the data it needs. We explored how the compression of the AI storm is forcing organizations to build much higher cybersecurity walls, relying on strict network segmentation and post-quantum cryptographic telemetry. And we finished by looking at how AI frameworks are orchestrating entire hierarchies of autonomous agents that are now taking active physical control of our local desktops.
It is a staggering pace of innovation. We're witnessing hardware optimization, cryptographic evolution, and autonomous software capabilities all converging at exactly the same moment in time.
It really is, and trying to keep up with it is half the battle. Now, for everyone listening, if you want more deep dives into these specific kinds of cloud security and AI insights, you absolutely need to follow the show Cloud and Cybersecurity News on Spotify. It's the best way to cut through the noise and stay ahead of the curve.
I want to leave you with a final thought to ponder as you look at your own architecture this week.
Okay.
Today, we learned about AI agents autonomously talking to other AI agents using standardized A2A protocols. We saw them writing their own background scripts to take control of user interfaces. Think about this. How long until the primary users of our meticulously optimized 400 gigabit cloud networks are no longer humans at all, but vast, silent fleets of autonomous software agents working entirely on our behalf?
Wow. We really are laying the tracks for the runaway train, and the train is officially driving itself. Keep learning, stay curious, and we will catch you on the next deep dive.